Hi, welcome back. In this lecture I want to talk about multi-qubit system, and then I will finish up this lecture talking about universal quantum gate sets. So far we have been talking about a qubit system and associated quantum gates. We talk about two qubit systems, and we saw how we can compose two qubit systems by taking the tensorial product of a two single qubit system. So the way to build quantum system is to use the tensorial product. We also saw the computational basis in the case of one qubit and the computational basis of two qubit system, for which we just take the tensorial product of the quantum state of computational basis for one qubit. So when we look at the computational basis in the case of n qubits, we just generalize what we did for the two qubit system. So we take the tensorial product of the computational basis for one qubit. So in the case of n qubits, the states that constitute the computational basis are here the following, where we take the tensorial product of the computational basis of the single qubit. As we did for the two qubit system, we omit the tensor symbol to write in this form here. We can also omit the bracket and this line here to arrive to this concise form that implicitly includes the tensorial product. And last but not least, we can write this from binary to decimal form. So for instance, if we have a 3-qubit system, we're going to have state 0, state 1, state 7. So 0, 1, and then 2 to the 3, that is 8 minus 1 is 7. A generic state of the system that we call upside will be then formed by amplitude multiplied by the computational basis vector. As for the single qubit and two qubit system, this amplitude must be normalized, so they are complex values. If we take the module and take the square, the sum must be 1. And the reason for that is these amplitudes are related to the probability of observing a certain state. If we decide to measure all the system qubits on the computational basis, then we will obtain probabilities for each state that is calculated as the square module, as I said in the previous slides. It becomes slightly a little bit more complicated if we only measure one of the qubits, let's say the jth one. Then we will obtain 0 with the probability of the sum of the square module for all the L belonging to J naught, where the J naught is the set of numbers whose the jth bit is 0. Remember that in this scenario, if you measure just one qubit or a set of qubits, then this quantum system will be still in the quantum state according to this distribution. We can do the same approach for calculating the inner approach of n qubit system. So if we express n qubit two n qubit system that are obtained by tensorial product, so psi and phi, we then calculated the inner product we have here by taking the inner product of the single component of our two quantum system. Also, we have multi-qubit gates that are applied to n-qubit system. In this case, the n-qubit gates can be identified with 2 to the n by 2 to the n unitary matrices. Then we can take these unitary matrices and multiply by the input vector of our n-qubit system, whose length will be 2 to the n. As you can imagine, at this point, we can determine these multi-qubit gates by taking the tensor product of single or two qubit quantum gates matrix formulation. And here you find what this what this means when having tensor product of matrices. There is one gate that is an extension of the CX or C0 gates. So if we have, for instance, 3 qubits, this will correspond to 3 lines. And what we can think as an extension of CC0 is a gate that has the following structure. So it has 2 control NOT represented on these 2 wires as a field, a dot, and a NOT operation on the last qubit. So this is very similar to the C0 gate we saw in the previous lectures. The only difference is that instead of having 1 control qubit, we are going to have 2. So this operation is conditioned on the value of these 2 qubits. In particular, if the values of this qubit and the values of this qubit is 1, then we will apply a NOT operation on the third qubit. So the CC0, so also called Toffoli, who is the scientist who devised for the first time this quantum gate. Well, it can be also taught as a classical gate. What it does is to apply a double control NOT operation. So we have 2 control qubit on the third qubit, and therefore the name. So we have C control NOT gate. The Toffoli gate is particularly important because by using it and by using an auxiliary qubit or bit, we can construct any classical Boolean operator. So we have AND, or we can implement any of these classical quantum gates, implementing a Boolean logic by using a Toffoli gate. And what is special about this? Well, what is special is that the Toffoli gate, as all the quantum gates, are reversible. So the Toffoli gate allow us to implement reversible version of classical gates that the direct implementation is not reversible. So we can make all our classical digital circuit reversible by implementing a classical version of the Toffoli gate. I want to finish up this lecture by talking about universal gates sets in quantum computing and why is it important. Well, as you know, at this step in this course, current quantum computer cannot implement every possible quantum gate, right? This will require a lot of work. However, any unitary operation can be decomposed as a circuit that uses a reduced set of primitive gates. So this reduced set that can be used to implement any quantum gates is called universal quantum gate set. It turns out that for any unitary operation, we can construct a circuit that implements its only 1 qubit and C0 gates. Right, so if we have a 1 qubit gates and C0, then we can implement all the other ones. So those gates are universal. This fact is actually crucial for our studies, for instance, for feature maps and variational forms in connection to the definition of quantum neural networks and other quantum machine learning models. This means that by using a certain set of quantum gates, we will know for sure that we can implement any other quantum gates. In addition to 1 qubit gates plus a C0, there are several other sets of universal gates. For instance, it can be shown that the 3 gates, Hadamard gates, the T gates, and the C0 also are a universal set. And this is just an example how to implement a CC0 or a Toffoli gate by just using a C0 and the T operation and Hadamard gate. This is the last slide of this lecture. Talk to you soon.